Visualization of the inner accretion disk and ring of fire. This is a supplement to video 6 to discuss an observer's view of the inner accretion disk and ring of fire, mostly for a non-rotating black hole. The final comments will be for a rotating black hole. This supplement will also discuss how photons get into the ring of fire. I assume that you have watched the video material on the accretion disk in video 5 and light trajectories for non-rotating black holes in video 6, though this supplement might stand on its own. This is an artist's conception of an accretion disk and jet. I discussed this image and some issues I have with it in video 6. The issue we care about for this supplement is that this image does not properly represent the bending of light near the black hole. The accretion disk would not look like a planar disk to an observer. Video 6 includes 15 minutes on how light behaves in the radial direction, so why light cannot leave the inside of the event horizon, and then 26 minutes on how light trajectories bend around the black hole. Let's see how the accretion disk should look to an observer, how visualization simulations should render the image. This image shows us stylistically where the light is coming from that reaches a particular observer, us. This black hole is not rotating. This accretion disk is flat and nearly edge-on to us. The accretion disk is hot matter that emits light in all directions, only a small fraction of which gets curved toward us, the observer. The portion of the accretion disk in front of the black hole shadow, here, looks normal. The light we see from there was emitted nearly radially outward, and those trajectories were not distorted much. Everything else is greatly distorted by the curved spacetime of the black hole. This image also shows the ring of fire here and here. Ignore it for now. We will cover it after the accretion disk. The accretion disk is shown here as 12 equal sectors at a given radial distance. This is a sector, this is a sector, this is a sector. There's 12 of them. 2 of the 12 sectors, the ones shown here, this one and this one, are behind the black hole. They're actually behind here, and are responsible for the light that we perceive above and below the black hole. Light that happens to be emitted vertically upward from the accretion disk behind the black hole gets deflected over the top of the black hole through 90 degrees and ends up traveling horizontally toward the observer. So the observer perceives that that light is coming from above the black hole. Likewise, for below the black hole, being light emitted vertically downward behind the black hole. I have placed 2 dots, red and yellow, on this image. These 2 dots are the same location on the accretion disk sector behind the black hole. So like here behind the black hole. Right of center. And they appear in different locations, here and here, to the observer. Here it's to the right and here it's to the left, but they're the same position on the accretion disk behind the black hole. The red dot is the top surface of the accretion disk, and the observer sees light that was emitted vertically upward there and curved over the top of the black hole. The yellow dot is the bottom surface of the accretion disk, and the observer sees light that was emitted vertically downward there and curved under the bottom of the black hole. You should pause and think a little about the different positions of the two dots before proceeding. Particles in the accretion disk are orbiting the black hole at high speed, half the speed of light at the innermost stable circular orbit, the ISCO, here, decreasing further from the black hole, so slower here. Some animation GIFs show the accretion disk rotating, though the time is not correct. The period would be milliseconds for a stellar mass black hole and minutes for a supermassive black hole. Let's take the accretion disk to be rotating left to right in the foreground, in front of the black hole. I place the two green arrows here and here to represent that the velocity of the inner ring at the ISCO is higher than for the slightly further ring. The ring that the observer perceives above and below the black hole will seem to be rotating faster. The yellow velocity arrows, because of the gravitational lensing curving those light trajectories. So the accretion disk is rotating this way, and here it's behind the black hole, but we see it as above the black hole. It's still rotating in this direction. And everything here is showing the underside of the accretion disk behind the black hole, but here we're seeing the underside of what is here. So as it's moving this way above, it's moving this way below, so we'll see it moving this way. Accretion disk material within this white bubble that I have drawn is moving directly toward us, and light from there will appear brighter and Doppler blue shifted to us, the observer. Accretion disk material within the brown bubble that I've drawn is moving directly away from us, and light from there will appear dimmer and Doppler red shifted. However, if the accretion disk temperature is millions or billions of Kelvin, I believe that a human observer would see it as bright blue-white in the visible spectrum, regardless of Doppler shift. This is a NASA animation of a rotating accretion disk. Don't take the rotation period or the low temperature colors as gospel, but notice the Doppler blue shift on the left and red shift on the right. If you look at the portions above and below the black hole, the impression is of counterclockwise rotation. Next, we will discuss the ring of fire, whose escaping light appears here as the narrow ring, here and here, bordering the black hole shadow here, not the event horizon, which is inside the shadow. For a non-rotating black hole, light can orbit the black hole circularly at 1.5 Schwarzschild radii. A non-rotating black hole has no preferential orientation in space. Light photons can orbit in any circumference or great circle of the ring of fire spherical surface at 1.5 Schwarzschild radii. For example, at this point, light can be moving in either of the yellow directions, either of the red directions, either of the green directions, or any circumferential direction at all. Likewise, for any other point on the spherical surface, light can move in any circumferential path. If there is an accretion disk, the ring of fire orbits have no orientation constraint relative to the accretion disk. Ring of fire orbits are unstable light orbits. Eventually, photons in these orbits either spiral into the event horizon or escape spiraling outward. I have no information about how long a photon remains in orbit or how many orbits it makes on average before escaping. The ring of fire location is 1.5 Schwarzschild radii, which I'm showing as this red solid line circle. When a photon escapes outward from the ring of fire, it does not abruptly change trajectory. The trajectory spirals outward. So if it was here, if the photon was escaping, it would spiral outward. The particular curvature of spacetime for the black hole curves the light trajectory such that it finally approximates a straight line at an impact parameter of 2.598 Schwarzschild radii, which is where the observer perceives the ring of fire and the boundary of the black hole shadow. That is the red dashed line circle that I've put here. This is close to the ISCO at 3 Schwarzschild radii, but there is a gap, which will appear black. So 1.5 is the actual ring of fire location. 2.598 is where an external observer will perceive the ring of fire photons as coming toward them. The black hole shadow will be black inside of 2.598. There will be a black gap between 2.598 and 3 is the innermost portion of the accretion disk. So this black apparently circular volume is the black hole shadow. This is where the observer perceives the ring of fire, which is the actual location is inside, but here's where we perceive the photons as coming from. Then there's a black gap. Then there's the ISCO, the inner edge of the accretion disk. All circular circumferential light orbits are possible in the ring of fire for an accretion disk feeding a non-rotating black hole. So photons are always available to escape and spiral and curve to present a perceived circular ring for any observer observing from any direction, I believe. This is different than the accretion ring, the accretion disk, which looks different looking along the accretion disk rotation axis face on, looking down face on, versus edge on, which is kind of what we're looking at, or a different angle. We're looking at a slight angle from edge on. Pause the video if you need to think about this. If we are content with how photons escaping the ring of fire would be perceived by an observer, let's discuss how photons get into the ring of fire in the first place. I think that there are two possible mechanisms, though I have not seen this described, so I could be wrong. This is an example trajectory of some matter that was at the ISCO here, rotating in this direction. It lost energy and angular momentum through friction or radiation, and it began to spiral toward and into the event horizon. Here it's spiraling and slowly, then a little faster, and here it crosses into the event horizon. This bit of accretion disk matter was very hot, so it radiates photons continuously in all directions. So it's radiating photons while it's here, and when it gets here, and when it's here. Most radiated photons escape the black hole system. Some photons spiral into the event horizon. As the matter crosses the ring of fire at 1.5 Schwarzschild radii, here, some of the photons emitted by the matter happen to be in directions such that those photons can now orbit at the ring of fire radius. So that's how some of the photons get into the ring of fire, I believe. A second mechanism for photons entering the ring of fire might be light from stars. If light entering the black hole system happens to have a trajectory with impact parameter of 2.598 Schwarzschild radii, that light may spiral into the ring of fire and then stay in the ring of fire for a while. It might then spiral into the event horizon or escape outward again by spiraling out to 2.598 Schwarzschild radii. If the impact parameter is slightly higher, light might spiral close to the ring of fire, then spiral back out and head in a different direction, as in the following diagram. So light was heading here, its trajectory got curved. In this case, it went around the black hole once, coming very close to the ring of fire, but it escaped the ring of fire, spiraled out, and it may be seen by some observers in that direction. So light started out this way, and an observer saw it coming in this direction. And this can happen from light coming from any direction and escaping to any direction. I have not seen any write-up describing a ring of fire without an accretion disk, so I may be wrong about this, about some of these photons getting into the ring of fire. Or it may be moot because gravitational lensing will produce star images all along the black hole shadow, which will be most visible when there is no accretion disk. Here is a simulation of gravitational lensing around a black hole with no accretion disk. You can see a thin white ring, at the boundary of the black hole shadow. This being the gravitational lensing of many background stars, appearing where the ring of fire would be perceived, the border of the black hole shadow. Here is one of the development simulation renderings for Interstellar. The final version they selected is brighter white, and it added haze to give the impression of painful brightness. This black hole is slowly rotating left to right in the foreground. So the accretion disk is rotating left to right in the foreground, and this black hole is also rotating left to right in the foreground. We could tell this because the black gap between the ring of fire and the accretion disk ISCO is larger on the left than on the right. This rotation is nowhere near the extreme rotation that Gargantua would need to produce the extreme time dilation for Miller's planet, but the director did not like the renderings with extreme rotation for the movie. Here, this accretion disk is in the equatorial plane of the black hole rotation and is nearly edge-on to us. For the rotating black hole, the ring of fire, with all possible circumferential light orbits, gets replaced with a discrete number of prograde, same direction as the black hole rotation, and retrograde, opposite direction, light orbits called the shell of fire. One prograde light orbit and one retrograde light orbit are in the black hole rotation equatorial plane, with the other light orbits being complex three-dimensional orbits. I don't know whether the shell of fire would look like a continuous thin ring as for a non-rotating black hole, but I believe that the light we see on the left half of the ring here is probably escaped from shell of fire prograde orbits, with the far left center being from the equatorial prograde orbit, which is pulled in toward the event horizon. The light that we see on the right half of the ring here is probably escaped from shell of fire retrograde orbits, with the far right center here being from the equatorial retrograde orbit, which is pushed away from the event horizon. However, I have not seen this described, so I may be wrong. This simulation from the development of the movie Interstellar is of a rotating supermassive black hole with no accretion disk. Notice how the black hole shadow does not appear as a circle here. It is scrunched on the left and pushed out on the right. The rotation axis would be vertical here, and the rotation would be left to right in the foreground. We don't see a ring or shell of fire here, but if there were an accretion disk, we would see the shell of fire at the border of the black hole shadow.